Yes, good evening. Good evening, friends. We have entered the third session of this inaugural function. And again, in the capacity of the member of the organizing team and chairman of Society of Indian Radiographers. Once again, I welcome you all for this third session of the inaugural function. The third session is the inaugural lecture, and this guest lecture is to be delivered by Mr. Tobias Gilk. The topic of the presentation is where and when the risks of the three electromagnetic fields in MR imaging. Dear friends, our dear friend, Mr. Tobias Gilk, is a certified MRSO and MRSE. He is a board member of American Board of Magnetic Resonance Safety. He is also a past member of ACR's MRI Safety Committee, that is American College of Radiology. He is the author of the 2007 ACR Guidance Document on MR Safe Practices, and also the author of the 2020 ACR Manual on MR Safety. Dear friends, Mr. Tobias Gilk has been a subject expert to many of the physical design standards for imaging facility safety. His paper on MRI safety, siting and zoning consideration is expected to be published in next few months. We should be happy to know that he is the founder and administrator of the Facebook MRI Safety Group with more than 25,000 members globally. Friends, I'm sure today's his talk will make many invisible things visible. We will learn to use informations for risk assessment and risk mitigation strategies to make MRI exams safer and more accessible to patients with implants or foreign bodies. With these words, I take this opportunity to welcome Mr. Tobias Gilk on behalf of you all for this inaugural guest lecture. Welcome you, sir. Welcome to India on virtual platform.
Thank you very much. It is my pleasure to be here. Thank you so much for the invitation. So today's presentation is going to be on the nature of the three electromagnetic fields that we use in MR imaging. As mentioned, I am a member of the ABMRS board. In addition, it's probably worth noting that my original training is that of an architect. I became interested in MRI safety nearly 20 years ago when doing design projects for MR facilities and identifying the ways in which the physical environment could help support safety best practices. From that point 20 years ago, I became interested in all things MRI safety, and I have dedicated the large portion of my professional life on that issue. Disclosures in terms of my interests. I am an employee of Radiology Planning, RAD Planning. It's a company that provides planning and design guidance for imaging facilities, imaging and therapy facilities. And then with my own consulting firm, Gilk Radiology Consultants, I have an ongoing relationship with Metrosense, which is a company that makes MRI safety products and offers MRI safety services as well. Whenever I'm speaking on behalf of MRI safety topics in general, I always include this disclaimer, that as a member of the ABMRS, I am precluded from talking about anything that is directly related to ABMRS examinations for MRSO certification or MRMD certification or MRSE certification. However, even prohibited from speaking on the exams and examination content, I do speak frequently on MRI safety concepts and foundational topics, and that's what we will be discussing this evening. So there are 4 elements, well, 3.5 elements that I intend to cover with you in the next 40 minutes or so. Identifying the 3 electromagnetic fields that are used in the generation of MR imaging, identifying the hazards associated with each of those 3 individual electromagnetic fields, identifying tools for visualizing the fingerprint, if you will, the spatial location of each of these 3 electromagnetic fields, which becomes extremely important in terms of being able to perform risk assessments for patients with implants and devices. And then the last thing I will talk about is one element of that spatial distribution, and that's the idea that there is precisely one of the 3 electromagnetic fields that we have the ability to collimate. We have the ability to change its spatial distribution and reduce the amount of the patient's tissues that are exposed, and that is RF, and that's only under a certain set of conditions. So that's sort of the broad outline of today's talk. Electromagnetic fields and risk management. When we perform MR imaging on anybody who has an implant, a medical device, a foreign body in them or on them, that implant or device or foreign body will be exposed to electromagnetic fields. That is the basis of MR conditional labeling for implants and devices, is we want to essentially define the known safe parameters for imaging a patient in whom there is an implant or device. And the 3 electromagnetic fields are static magnetic field, time-varying gradient magnetic field, and radio frequency magnetic field. We're going to break these 3 electromagnetic fields down and talk about them individually because they are independent of one another. Successfully addressing risks associated with static field does nothing for gradient magnetic fields, and that does nothing for radio frequency magnetic fields, with a couple of exceptions. But in general, we should approach each of these as being completely independent electromagnetic fields, as they are, with completely independent sets of risk assessment and risk mitigation. So the first step in this is to identify what risks are associated with which of the electromagnetic fields. And the second is to identify the region or the volume where these electromagnetic field hazards, the risks associated with them, exist, where they are present, where we need to be concerned about them, or conversely, where we don't need to be concerned about them, where we can, to some extent, ignore them. So with that, let's start with our first of the 3 electromagnetic fields, the static magnetic field. And for that, there are really 3 predominant risks associated with the static magnetic field. Torque, the property of magnetic materials in magnetic fields that they want to twist, they want to align with the poles of the magnetic field. Translation, or the missile effect, which is the property of a magnetic or magnetizable material that wants to be drawn towards the highest strength part of the magnetic field. And then the Lenz effect. Lenz effect is a function of Faraday's law of induction, which actually does, in some instances, the reverse of what translation does. The Lenz effect actually retards, slows, prevents motion towards the magnetic field. And that's caused by a different set of criteria or influenced by a different set of criteria than is translation and different than torque. But it's an important safety factor that we need to be aware of when we're bringing patients with implants device or even just objects or materials close to the MRI scanner. So let's break these three risk factors from the static magnetic field. Let's break them down a little bit further. Torque. What are the contributing effects that make torque-related risks greater or lesser? Well, torque is a function of a number of different factors. And let's start with the ferromagnetic properties of the object. And here I'm going to be speaking about the contributing factors of objects or devices that we bring into the MRI area. We can't modify the static magnetic field of our MRI scanner. It is what it is. So I'm going to talk with you about identifying the nature, the characteristics of materials that we might be bringing towards the MRI and how they contribute to the risk. The static magnetic field is the principal driver from an electromagnetic force, but it's the interaction between that electromagnetic force and the objects, the materials. So first among them is ferromagnetic properties. The more magnetic or magnetizable that an object is, the greater the potential for that object to experience torque. A non-magnetic material, aluminum, titanium, these materials, copper, will not experience meaningful torque. Most alloys do have a little bit of other metal materials, and it may have some ferromagnetic material in it. So there may be a nominal or negligible amount of ferromagnetic material that might introduce torque. But fundamentally, what we're looking for is a magnetic or magnetizable material. These are typically, or most frequently, iron, nickel, and cobalt are the three most prevalent ferromagnetic materials. The shape of the object. So torque essentially wants to take an object and wants to rotate it to align with the poles, the north-south pole of that magnetic field. If an object is spherical, such that it doesn't have a lever arm, then the simple shape of that object, the spherical shape, essentially defeats the function of torque, the size of an object. So a small linear object like a needle will exert a certain amount of torque, but you take a larger object, say a steel rod that's 0.5 meter long, the size of the object will directly impact the quantity, the magnitude of torque that is possible in that scenario. So the more ferromagnetic material, the more ferromagnetic the material is, I should say, the more elongated or needle-like, rod-like, as opposed to sphere-like, the greater the potential for torque force, and the longer that object is, the greater the potential for torque force. So that's torque or rotational force, and these rotational forces will act on magnetic or magnetizable materials even within the human body. So simply because it's an implant or device that is inside the body does not mean that somehow the magnetism isn't going to get to it. Let's look now at translation or missile effect related forces. You'll notice some of the same elements recurring from our torque forces. The ferromagnetic properties of the material, the more magnetic or magnetizable the material is, the more likely or the more pronounced the translational force, the magnetic attractive forces, will be on that object. The shape of the object, for a different set of reasons, an elongated shape, like with torque, an elongated shape will have greater potential for translational force. With torque, it's essentially a longer lever arm, and the longer your lever arm, the more force you can exert effectively, because the lever is essentially a force multiplier. For translational force, the longer the object is, the easier it is for that object to develop discernible, distinct magnetic poles, a positive pole and a negative pole at one end of the object or another. The size of the object. So again, the further apart those poles can be on a linear object, the more cleanly an induced magnetic field can be formed in them, and then the mass. All of these things, the greater the mass, the more force, because force is mass times acceleration, and the magnetism produces or provides the accelerative force, and that acceleration times the mass is what ultimately drives the force. So think of each of these things as a factor in a multiplication equation. Ferromagnetic properties times the shape times the size times the mass. And if any of these objects is zero, right, a number times zero equals zero. So if in this instance we say we have a truly non-ferromagnetic material, so the ferromagnetic nature of that material is zero, then it doesn't matter if the shape or the size or the mass are significant in terms of risk factors for translational force. If all of those things, if it's a large mass, it's long and linear, that might be significant multipliers. Because we're dealing with a non-ferromagnetic material at its core, that factor is zero times the other factors, and then the net is, the sum is zero. And similarly for torque, if we have zero multipliers because we have a spherical shape, which even if we have a ferromagnetic material, of 1, maximum possible risk factor times a pure sphere, a 0, 1 times 0 equals 0. So it's important to identify the roles, the contributing roles that each of these potential factors play. Lenz force. Lenz force is significantly different than the preceding two. It behaves under different properties. So Faraday's law of induction says a moving electrical field produces a magnetic field, and the inverse of that is true as well. An object moving through a magnetic field generates an electric field. And you can think of this as sort of mirrors upon mirrors and an infinite regression, infinite reflection type of situation. If we continue to introduce electrically conductive materials into a magnetic field, those electrical conductors, if we move them through the magnetic field, they will generate an electrical current in that material. That electrical current now generates a magnetic field. Interestingly, when you have a Lenz effect, when you have an induced electrical field generating its own magnetic field, that magnetic field is formed in opposition to the primary magnetic field. What this means is if you have a good electrical conductor, a material that offers low resistance to electrical conductivity, and you move it through the magnetic field, particularly the portion of the magnetic field with the higher spatial gradient, then the induced voltage in that material will generate an oppositional magnetic field and will retard the motion, will seek to stop it from moving towards the magnetic field. So it does, in some ways, the inverse of what the translation force. Translation force draws the object in, lens force prevents it from being drawn in. The three factors that influence an object or material's propensity to experience lens force are the electrical conductivity, not the ferromagnetic properties, but the electrical properties of this material, and then the shape and the size. The shape, whatever the shape is, this is really orientation. It needs to be set up so that the magnetic field lines essentially are perpendicular to the face of the object. So if we take my mobile, for example, right? We take an object like this, and these are the flux lines. These are the magnetic orbits. If it's edge on, they sort of pass right by. However, if it's perpendicular and they strike the object, that's when that orientation is the orientation in which the induced electrical fields, which then subsequently secondarily induce a magnetic field, that's when that experience is likely to be greatest. And then the bigger the object, so, from a mobile to something larger, a laptop size, the bigger it gets, perpendicular to the movement of the magnetic flux lines, the greater the lens force will be identifiable for an object of similar electrical conductivity. So what do we get? What information do we get from our MR system manufacturers that helps us to identify potential risks? And here again, I'm going to go through these in sequence, and I'm going to start with the static magnetic field. We actually get some really useful information from our equipment manufacturers, our vendors. So this slide right now is an ISO Gauss plot. It's showing the Gauss lines around the MRI. So in this particular image, so this is a bird's eye view, a plan view of the MRI scanner, and it's showing the static magnetic field lines as they surround our MRI scanner. And on here, if you tilt your head sideways, you can see we have labeled the 5 Gauss, 10 Gauss, different static magnetic field values. Excuse me, the furthest one out is the 0.5 Gauss. So essentially that's atmospheric levels. That's the point at which we really can't discern static field originating from the MRI versus the Earth's own static magnetic field. So this is field strength alone. The next diagram is for magnetic spatial gradient or spatial field gradient. And this diagram is essentially showing the rate of change as we move from point A to point B, and we have a static magnetic field value at point A, and we have a static magnetic field value at point B. What is the rate of change between those 2 points? And static magnetic field gradient is extraordinarily important, because in terms of what the magnetic field's contribution, it is the single greatest part contributing factor for translational forces, the attractive forces. So this diagram is showing an ISO gradient values. This chart on the right-hand side is the center of your MRI scanner, and then those curved lines represent the mouth of the bore. In almost all MR systems, these spatial gradient values are radially symmetric, which means we could be looking at a coronal view, we could be looking at a sagittal view of the mouth of the bore, and it would be equally true in any orientation, looking at the mouth of the bore. So if we were to compare information from the equipment manufacturer with three-dimensional views. And for this, let's make sure we look at the slides. So these are courtesy of Dr. Canal and Magnet Vision. What we're looking at right here are the values of a static magnetic field. And this is for a 3T magnet, although you can see on the screen that there are locations in a 3T magnet that are greater than 3T. And here we switch to spatial gradient. And you'll see there's zero spatial gradient or zero colorization in the center. And when we do point values, you can see that essentially it's functionally zero in the middle of the magnet. But you can see that there are regions near the mouth of the bore where the spatial gradient values are quite significant. It's incredibly important to have a good understanding. Let me see if I can just restart that animation. Here we go. Now you know what I'm describing. So the fuchsia, the pink, is 3T values. The white is where it actually exceeds 3T. It's really important to have an accurate understanding of the spatial distribution of the magnetic field, both static field and the product of the static field, the magnetic spatial gradient, because when it comes to reviewing MR conditional implants or devices, we really don't care what the patient is going to be exposed to. We only care what the implant or device that has an MR conditional threshold value, we only care what that one is going to be exposed to. So that's static field, the B0 and the magnetic spatial gradient. What about the imaging gradient, time-varying gradient magnetic fields? So what are the risks associated with the time-varying gradient? Time-varying gradient produces neuromuscular stimulation, or it's capable of producing direct neuromuscular stimulation. Patients who describe peripheral nerve stimulation, the tingling feeling, a buzzing feeling, the feel like maybe there's something small crawling on their skin, metallic taste in extreme conditions for patients who are really sensitive. Time-varying gradients, I have a single anecdotal account of time-varying gradients actually triggering magnetophosphines, triggering flashing light sensation in the eyes. That is a product of neurostimulation, direct neural excitation from the time-varying gradients. Time-varying gradients can produce a negligible amount of heat, but the principal concern that we have for them is direct neurological stimulation. The second concern we have, it pertains to vibration. If we have a large enough electrically conductive object, the oscillations of the magnetic field for the time-varying gradients, they actually produce a Lenz effect, just like the static magnetic field moving through the static magnetic field. Stationary, in a time-varying magnetic field, we can get Lenz effect results, forces. Because the time-varying gradient oscillates so quickly, essentially we may be turning on, turning off, turning on, turning off, turning on, turning off in very rapid succession, a force that is acting on a ferromagnetic or even simply electrically conductive material. Now, the size of the material, the size of the object is directly related to the potential for vibratory forces. That plus the vibratory sensation, if it's in a very sensitive tissue with lots of nerve endings, then it may be more prone to the patient, may be more prone to detecting these sources, these stimulations. What are the elements that contribute to the potential for each of these risks? So neurostimulation, the electrical conductivity of an object or material inside the body of the patient. Human tissues are electrically conductive. Modestly, they're not great electrical conductors, but if we introduce a much more effective and efficient electrical conductor, that increases the potential for neurostimulatory effects. If that conductor has insulation over it, in other words, a lead of one sort or another, that creates a concern, because the time-varying gradients as oscillating magnetic fields, a magnetic field doesn't see the insulation. It's as if it's not there. It passes immediately through it, and then it hits a nice, very efficient conductor, electrical conductor, at which point it stops behaving like a magnetic field and it starts behaving like electrical current. So the size, the length of the object is the next risk factor. So if we have a lead that winds through the patient's tissues, right, and we are imposing time-varying gradient energies across a large portion of the patient's anatomy, this lead has the potential to essentially be exposed to time-varying gradient over a large area, absorb that energy over a large area, but then once it turns into electrical current, how do we respond to that? What happens? Well, once it's electrical current, the only way that it escapes is through an uninsulated part of the lead. Now, normally the terminal ends of a lead will be uninsulated, which means we're collecting over a large area and we're depositing in a small area. Think of a funnel or a lens, where we collect material on a large area and then we deposit it in a small area, and we increase the concentration of, if it's a funnel, liquid, if it's a lens, light. And this is essentially an analogous function, only we're collecting neuromuscular stimulatory energies from a large area and we're depositing them in a small area. If we deposit them in a particularly sensitive structure, that is potentially bad. Now, the position within the bore makes an enormous difference, because we don't distribute time-varying gradient energies uniformly throughout the imaging process. And we'll look at sort of the specific location associated with that here in just a minute. The other risk factor is vibration. And so vibration is a product of the electrical conductivity of the object or material that may be vibrated, its size or length. And the larger an object is, particularly that is capable of supporting a circuit of current. So a large circular object would be amongst the worst. That represents the greater potential risk factor. And then the position within the bore, because just like the neurostimulatory effects, the vibratory effects are a product of the magnitude of the time-varying gradient energies, which vary depending on the location. So let's talk about what those locations are and how they vary. So information from your equipment manufacturer, it varies significantly. This is an illustration that this one happens to be from Siemens. Siemens actually now, as a default, as I understand, provides gradient amplitude information at 3 positions in the bore. And these 3 curves represent 20 centimeter cylindrical volumes centered about the z-axis, 20, 40, and 60 centimeter cylindrical volumes centered about the central z-axis. And you can see from the height of those various curves, as you move from center out radially, the closer you are to the bore wall or bore ceiling, the higher the magnitude of these energies. The maximum energy location in this particular magnet occurs somewhere around the 35 centimeter superior and inferior, because this is symmetrical about the central isocenter z-axis points. As you move both inferior and superior from isocenter, and you move radially, this is where you will experience the greatest time-varying gradient amplitude. Once you get beyond that 30, 35 centimeter superior-inferior distance, now you're 40, 50, 60 centimeters superior or inferior, you can see that the time-varying gradient energy, the amplitude, drops off precipitously after that. So how does that compare with the three-dimensional view? So here we're looking again, and again, thanks to Dr. Kanal and Magnet Vision. And here you can see, and with the cutting planes, we actually have X, Y, and Z views. And if we move the axial plane, you can see that it's radially symmetrical. The amplitudes, the maximum possible amplitudes of time-varying gradient. And again, let me see if I can simply replay that slide. I think it's very useful to see. So maximum gradient amplitudes. This patient positioned for a brain, the maximum gradient amplitude that they will experience, that their tissues will experience, is in the upper arm. And this is very counterintuitive, particularly to people who come to MR from an X-ray background, where we're very careful to make sure that the energies associated with capturing the image only strike the anatomy where we're capturing the image. MR is different because we the maximum energies are in locations other than where we're capturing the image, and we have very little ability to modify that. We can't modify it at all for the static field. We can't modify the spatial distribution at all for the time-varying gradients. There is, however, one electromagnetic field that we do have a little bit of capacity, and that's the radio frequency. But before we talk about the capacity to control or constrain the spatial distribution, as before, we're going to talk about the risks and risk factors. So radio frequency energy is the principal source of diffuse thermal loading, warming of the patient. Under certain circumstances, that diffused energy distribution or deposition can be focally concentrated, and that can result in focal heating or burns resulting from the radio frequency energies. The elements that contribute to diffuse warming throughout the body of the patient are the levels, the intensity of SAR or B1 RMS, the patient mass. So particularly if we're using SAR, right? 2 watts per kilogram for an infant and 2 watts per kilogram for a morbidly obese patient are the same because they're both 2 watts per kilogram in terms of SAR, but that, discounts or does not contemplate the mass of the patient themselves and the mass contribution. So 2 watts per kilogram times 10 kilograms is 20 watts. 2 watts per kilogram times 100 kilograms is 200 watts. So the mass of the patient has an immediate and direct influence on the total amount of RF energy that's being used for a study. So patient mass contributes directly to the potential for diffuse patient warming. Additionally, the transmitting RF coil, the amount of tissue inside the volume of the RF coil has a direct impact on this. Now, generally speaking, and we're not concerned about diffuse thermal loading because I am not aware of reported incidents of patient harm from core temperature elevation. There are many, many, many accounts of patients being uncomfortable by core temperature elevation, but I'm not aware of accounts of patients actually being injured by core temperature elevation in MR. What there are multitudes of reports of is focal heating. So the risks associated with focal heating, or the contributing factors for focal heating, is everything I mentioned for diffuse heating, plus the proximity to the transmitting RF coil. It is exceedingly important that radiographers know what is doing the transmitting for any particular study. The presence of electrically conductive material in the bore with the patient. This can be from the patient's own clothing. This can be from EKG leads or patches, or pulse oximetry leads. This can be from implants and devices internal to the patient themselves. The electrically conductive materials, like as I described with time-varying gradient, they accept energy over a large area, and then once it penetrates the insulation, particularly for leads in insulated materials, it can only then deposit the energy at the uninsulated bits, typically the terminal ends of a lead. So electrically conductive materials, particularly insulated materials, can represent significant risk factors. And then skin-to-skin contact, because like with time-varying gradients, the oscillating radio frequency fields induce currents in the tissue of the patient. Not electrocute you, shock you currents, but enough current that when they meet a location of electrical resistance, then that point of electrical resistance can form electrical resistance sufficient to produce local warming. And that local warming can quickly turn to tissue damage. And the working theory is that this occurs in the fatty layer, or the muscle fat interface. And one thing that's important to note is that human beings do not have nerves, temperature, or pain sensation in the subdermal fat layer. So the thinking is that these large caliber body loop burns, the patient is being burned, and yet they have no real-time awareness of the fact that that's happening. And that's for skin-to-skin contact. So what do we know from our manufacturer about the spatial distribution of radiofrequency energies? Unfortunately, not very much. This is an example, this particular example is from GE. Like the time-varying gradients, spatial distribution information from the vendor, this only shows half of a distribution curve. I didn't do it on the previous, but imagine this happening to the time-varying gradient information also. If we show what happens in both halves of the bore, and that's actually difficult to see. So I'm going to overdraw the curve, and then the gray shaded area is the length of the bore. Now this curve is showing proportional energy, and dead center in isocenter, it's showing the proportion being 1 maximum. And then as you move superior or inferior along the z-axis, you can see that the RF energy drops off dramatically. So what does this diagram tell us? Well, this diagram tells us that radio frequency energy is maximum at isocenter, and that it drops precipitously as you move away from isocenter. Unfortunately, that's not the least bit accurate. So here again, we go to magnet vision and we turn on the body coil. This is RF energy from the body coil. And you can see that actually the maximum is 25, 35 centimeters superior and inferior, radially positioned. And let me see if I can restart that slide again and show that animation one more time. So the green area is, mostly the imaging volume. And again, as with the time-varying gradient illustration, here I have the patient positioned for a brain, and you'll note that the greatest likelihood of RF burn, if we're using the body coil for transmit and we're doing a brain on this patient, greatest risk of burn is at the patient's shoulder or upper arm, which is, particularly for folks who come from an X-ray background, completely counterintuitive. The greatest risk of injury is not necessarily in the anatomy where we're taking the image. So I mentioned a couple of times previously that we do have one option for collimation, for restriction of the physical spread. And that's if we use transmit-receive coils. So in the next illustration animation, I'm going to show you, and we're going to switch back and forth between the volume that receives RF radiation when we use the integral body coil built into the wall of the tube of the MRI versus using a transmit-receive head coil. Let's start that animation. We start out with the body coil, and we switch to the head coil. And as I switch back and forth and change the view, you can appreciate just how much more constrained the RF energy deposition is between these two coils. And one more time, I'll see if I can restart that illustration. And we go back and forth between body coil for transmit and a local transmit receive coil. And as you can see, that makes an enormous difference in the amount of tissues that are potentially exposed to radio frequency energy. So in summary, with respect to the information you get from your MR system manufacturer, when it comes to the static magnetic field, both in terms of the field strength and the spatial gradient information, in my opinion, the manufacturers do a very good job of getting us appropriate information for static field. For the time varying gradients, they do a decent job. I would like to see more detailed information, but that information is generally pretty useful. Radio frequency energy, on the other hand, in the US at least, accounts for the majority of reported MRI accident adverse events that are reported to the US FDA. And I think one of the reasons it's probably most frequently reported is because the information available to MRI providers, to radiographers and radiologists about the spatial distribution of RF is incredibly poor. And if we don't have accurate information about the magnitude or the spatial distribution of that, we're not going to take appropriate steps. When you see the spatial distribution of a transmitting body coil, all of a sudden, the importance of providing padding from the bore walls becomes immediately clear. And I think we really need to demand of our manufacturers greater information, particularly for RF-related magnetic fields, so that we have a better understanding of their spatial distribution. With that, I'd like to point out a couple of resources for you. The Magnet Vision app that I used, it's only available through for Apple devices. Dr. Canal has previously said, please don't buy it. He has set the price at some ridiculously high level to discourage people from buying it. He actually gives it away when he does his MRI safety training courses. If you have an opportunity to learn anything from Dr. Canal, I can't recommend it highly enough. Plus, if you attend one of his MRSO, MRMD courses, he gives you the Magnet Vision and you can play with the visualizations that I illustrated pieces of. Additionally, if you are interested in conversations about MRI safety, I wholeheartedly recommend that you join the Facebook MRI safety group. As mentioned in the introduction, we have 20 some odd thousand members from all over the globe who actively participate. Today is the last day of MRI Safety Week, and we've been doing case of the day discussions every day this week, and the conversations, I'm sure, will continue with very interesting subject matter as we go forward. So with that, I wish to thank you very much for your time, for your attention, discussing where and when, the 3 risks of electromagnetic fields. If any of you have any questions, I'm happy to entertain questions as best we can now, but you are also invited to contact me. You can find me by my name on Twitter, on Facebook, and I invite any questions that there may be. Oh, here we have a question. If we input patient mass more than actual before starting the scan, will it help get better signal? What would be the risk-benefit factor in this decision? I would very strongly encourage you to use the appropriate, correct patient mass, because when you increase what you tell the system, when you increase the mass above the patient's actual mass, what you are telling the MR system to do is to produce more RF energy, to introduce greater RF power into that study, into that patient. That does, yes, provide for greater signal, but it does so at the risk of increasing the amount of RF power, increasing the diffuse thermal loading, and increasing the risk of focal heating for that particular patient. MR systems, some MR systems will actively monitor RF energy that doesn't actually strike the patient and will in real time adjust RF power. But even with that as a safeguard, I would recommend not modifying, not altering the actual patient mass, and use the actual patient mass for the purpose of that study. It was an excellent question. And while I was sharing my slides, I was unable to see if people had put up questions during the slide presentation. So if you put up a question previously, please repeat it and I'll answer as best I can with the time we have remaining. Thank you very much to everybody who's saying thank you to me. I am grateful for the invitation and grateful for the opportunity to share this information with you. Impact of a peripherally placed metallic implants on image quality. So anything electrically conductive is going to Faraday's law of induction. As we have an oscillating magnetic field, it will induce an electrical current in that object. The electrical current will generate a secondary magnetic field. Anything electrically conductive will generate an artifact. So the magnitude of the artifact will be a function of the object's electrical conductivity and the object's ferromagnetic properties. You will get a much greater artifact from a magnetic or magnetizable material than you will from a non-magnetic, non-magnetizable material, such as titanium. However, because titanium is a metal and all metals are electrically conductive, Faraday's law of induction tells us that there will be a magnetic field about that titanium object or material. The degree of artifact is going to be a function of not only the material, but the scan that you're running and its sensitivity to disturbances in the magnetic field, susceptibility related disturbances. So gradient echoes are going to be more susceptible to artifact disruptions than, say, a fast spin, turbo spin echo. They have a greater sensitivity to metallic susceptibility. That's an excellent question. How do we do planning MR room installation? What factors to keep in mind? I'll point you to one resource that's available right now, and another resource that I understand will become available a month from now. The immediately available resource, I would point you to the ACR. You can either use the 2013 ACR Guidance Document on Safe MR Practices or the more contemporary 2020 Manual on MR Safety. They both have the same appendix, and it's, forgive me if I don't get this exactly correct, but one of the appendices in that document is MRI suite safety planning approaches, something along those lines, and that it essentially, it walks you through the sequence of patient experience. So check-in and screening form and physical screening changing and clinical review of a patient's screening information. And it essentially takes you through the sequence as experienced by the patient, and it describes what are the physical features of each of those spaces that are important to consider for design purposes. So the ACR information is helpful, but it is principally narrative. It doesn't provide, diagrams or illustrations and that sort of thing. The other resource that I understand will become available September 1st is a new publication that I was fortunate enough to help author, and this is for the United States Department of Veteran Affairs. In the United States, there is a separate hospital and healthcare system for military veterans, and that system is publishing a new design document. It's called the Design Guide, that will be for all radiology and nuclear medicine, including MRI. And that will, that document, when it comes out, will include information about MRI suite planning, layout, prototypical suite designs, including information for architects or engineers using three-dimensional computer-aided drafting drawings for that. So let me take a final question because I don't want to disrupt the rest of your program. Is what I explained applicable to OpenMR as well? Generally speaking, yes. There are a couple of important things to note that are substantially different with OpenMR, or vertical field systems. So we have tube systems, and then we have the stacked disks systems, the vertical field OpenMR systems. Those vertical field systems, by nature of the architecture of those magnets, they will have higher spatial gradients than will tube format systems. Additionally, of potential concern is the fact that the radio frequency energies are directed at the patient from a different orientation than the tube format systems. Radio frequency heating of an object or material is a function in part of the object's orientation relative to the direction of radio frequency energy directed at it. So an object where the radio frequency energy is directed edge on, a significant proportion of that radio frequency energy can miss, but if the radio frequency energy is directed perpendicularly, then it's easier for greater radio frequency energy introduction into that object or material. Because of the difference in configuration of the radio frequency transmit sources in vertical field open magnets, it can change the likelihood of an object or material heating based on its normal orientation inside the body of the patient. So I hope that helped. I hope that the entire presentation was beneficial to you. I would like to thank the Society for Indian Radiographers for inviting me and this opportunity to present to you. If you have questions beyond our allotted time frame here today, again, you can search me on social media and share your questions with me there, or join the Facebook MRI safety group and share your questions there. And I will do my best to provide you whatever information I can. Gentlemen, thank you so much for the invitation. I am honored to have been a part of this inaugural meeting. Thank you. I understand I left a bit abruptly. Please forgive me.
Mishra sir,
Ah,
can you hear me?
Yes.
yes, I can hear you. Camera is off.
Yes, sir. Yes. Okay, no issue. You can speak, sir.
Yeah. Anyway, so 70 minutes, knowledge packed 70 minutes from Tobias Gilk, sir. Sir, let me congratulate you for one of the best presentations which I was fortunate to attend in MR safety. Sir, you will be happy to know that not only the senior radiographers from India, but also thousands of student radiographers were attending your lecture. I was also one of them, and I really congratulate you on behalf of Society of Indian Radiographers to accept our invitation to give the guest lecture in the inaugural function of our X125, the PowerPoint presentation competition for medical radiography and imaging technology students. Thank
It is my pleasure. It is my honor. MRI safety is something that I care deeply about, and I am grateful for the opportunity to share this information, share my knowledge with radiographers, radiologists around the globe. I was fortunate enough in January to give a smaller presentation at the IRIA meeting. Yes, in January, and I think that this information is hopefully useful and valuable to radiographers, radiologists alike, everywhere about the globe. So thank you for the opportunity to share something I care deeply about.
you, sir. Stay safe, sir. Take care. Meet you
You as
sometime.
well.
Thank you. Thank you
Thank
very
you.
much, sir. Good day for you and good night for all our Indian friends. Thank you. Thank you, friends. Let's finish this third session of X125 inaugural function. That is the PowerPoint presentation for medical radiography and imaging technology students. Meet you on 9th of August at 2 p.m. Thank you. Thank you. Thank you very much.